Swayam Prabha. Digital India. Educated India.
So, welcome to today class of nonlinear vibration. Today we are going to start module 4 of this nonlinear vibration course. So, in this module we are going to study regarding the single degree of freedom nonlinear systems. So, in single degree of freedom system, so we will study regarding the free vibration, force vibration. So, in case of force vibration, so we will study if the system is weakly nonlinear or the forcing is weak or the forcing is strong. So, strong forcing and weak forcing, both the two types of things we will study, and particularly we are going to take the example of Duffing equation and some other types of equations which are used in this single degree of freedom nonlinear systems. So, already we are familiar with different type of response. For example, so we know this equation have a fixed point response, periodic response, quasi periodic response and chaotic response. So, 4 different types of response we know. So, first one is the fixed point response, second one that is the periodic response, the response of the systems may be periodic, and then quasi periodic response. Quasi periodic is also known as aperiodic quasi periodic response, and finally we know the response may be chaotic, and this response actually we can characterize by using this time response plot. So, that means, so we can plot this response, for example, the response is x. So, x t versus t. So, this is the time response, or we may plot the phase portrait. So, in case of phase portrait or state space, so in case of phase portrait generally we plot x versus x dot, that is the displacement versus velocity. So, using this displacement versus phase velocity we can tell this as the phase portrait. Also we may plot the Poincare section. So, by using this Poincare section also we can characterize. So, in this module I will tell you how we can derive or find the Poincare section, also how we can characterize, particularly to characterize this chaotic response we may require some other characterization, for example, Lyapunov exponent. So, all these types of response and how to characterize those things also we will study while studying this single degree of freedom system. So, already we are familiar with the equation and solution method. For example, so we know we can solve these equations by using these numerical methods, or we may go for this perturbation analysis. So, for the Duffing equation, so today I have checked the literature in this Scopus and you can find, so there are more than 3400 papers found in Scopus related to Duffing oscillators only. So, in 2010 you can find 10 publications, 20 around 134 publication, 19 165 publication, 18 157. So, more than 100 publications are you can find in each year from 2012 to last year itself. So, this year also in 2020, this 10 is in 21, actually now it is November 20, but already in 21 10 paper have been, those will be published in 21 10 papers have already been published related to doping oscillator. So, the authors, most prominent authors who have worked in this field are W. Su, H. Tamura, A. C. J. Luo, A. Sueka, J. H. He, W. Q. Zhu, A. Y. T. Leung, K. Oden, S. T. Zhu and R. Ansari. So, you can find many other authors are also working in this field. So, as more than 3000 papers are just simply on doping oscillator is found. So, you may be knowing, so how useful this study is. So, there are several studies available on this thing. Some of the prominent papers or some of the paper in this last 2 years which I have marked. So, you can see in these slides. So, for example, this residual series representation algorithm for solving fuzzy doping oscillator. So, this doping equation now has been modified in many different way. For example, this fuzzy doping oscillator you can find here. So, this similarly this doping oscillator is used for this energy harvester purpose also, you can see in this paper, piezoelectric doping energy harvester. So, one can model a cantilever beam as a cantilever beam with this follower load also as a doping oscillator, which is studied in this paper. So, then a simple cubication method for approximate solution of nonlinear Hamiltonian oscillators. So, here also the system is considered as that of a doping equation. So, you may study this continuous piecewise linearization method for approximate periodic solution of a relativistic oscillator, and then a generalization of the S function method applied to a doping van der Pol forced oscillator. So, along with the doping oscillator you may add van der Pol oscillator, you can add Matthew oscillator, Matthew equations. So, in recent time, so you can find a number of paper along with the doping oscillator also. Similarly, you can see this paper non-existence, existence and uniqueness of limit cycles for generalization of van der Pol doping and Rayleigh doping oscillator. So, you already were familiar with this van der Pol oscillator where one can get the limit cycle. So, one can add this doping oscillator along with doping with this van der Pol equation, so that one can get this van der Pol doping equations also. Similarly, Rayleigh doping oscillator also one can get. Similarly, this damped super linear doping equation with strong singularity for repulsive type. So, this is a very recent paper. Similarly, on the integrability of some forced nonlinear oscillation. Then chaos transition of the generalized fractional doping oscillator. So, this is another interesting topic which is advanced topic related to the simplified doping oscillator, that is your fractional order. So, in doping oscillator, so some fractional order derivative is added to make it fractional doping oscillator. Also, one can add the time delay in this doping type of equation to get this delayed oscillator in case of the doping equation also. So, this paper you can see modified multiple scale technique for the stability of the fractional delayed. So, here both fractional and again delayed nonlinear oscillator. So, then analysis of fractional doping oscillator, FPGA implementation for a chaotic digital receiver using doping oscillator array. So, this doping oscillator equations can be applied to almost all the fields of engineering and science. In biological systems also you can apply or model some of the systems as a doping oscillator. A simple spring mass system. So, to realize a doping oscillator, so you can take a simple spring mass system where, so this is a simple spring mass system and if you are considering the spring to be nonlinear, then this equation can be written. So, for example, this is x you are writing. So, this spring you are considering to be nonlinear, then this equation can be written in this form mx double dot plus kx plus, let me write k and k1. So, plus k1 x cube. So, if I am taking cubic order nonlinearity and if a force is applied to the system, so for the damping you can write C x dot equal to F sin omega t, where F is the amplitude of the forcing, omega is the frequency of the forcing, and here you just see this term k1 x cube. So, these represent the nonlinearity, cubic nonlinear, and this is the forced doping equation. So, if the forcing F equal to 0, then this is the doping equation for a free vibration type. So, if the damping term is also neglected, if the damping factor is C is taken to be 0, so then this equation reduced to mx double dot plus kx plus k1 x cube, that is a undamped doping oscillator. So, this undamped doping oscillator mx double dot plus kx plus k1 x cube here. So, if this k1 is greater than 0. So, if k1 greater than 0, so this is hardening type, that is positive, then this is hardening, the spring is said to be hard spring, and if k1 less than 0, the spring is said to be soft spring. So, you can have a soft type of spring. So, if k1 is negative and if k1 is positive, then you can have hardening type of spring or hard spring. So, this doping equation can be modified in many different way. So, for example, this damping term, if we can add that of a van der Pol type, then so it will be known as van der Pol doping equation. Similarly, if a fractional order term will be added, so for example, I will add another term, that is dp x. So, here the pth order fractional order derivative, if you are adding, then this will be fractional order doping equation. So, this way many different type of oscillators can be generated out of this simple system. So, here the forcing also may be divided into or can be taken as a simple harmonic forcing, or it can be taken in many different way. Two frequencies can be taken or multiple frequencies can be taken, or stochastic type of forcing can be given also to the system. So, one can analyze the simplest type of spring mass damper system or write down this equation of a simple spring mass damper system in many different ways. Also, you may note that by taking different value of this m, k, k1, c and f and omega, so different type of response can be generated. So, already you are familiar when this k1, c and f are 0, so the system is that of a linear undamped system, and in case of linear undamped system, the response is, so already you are familiar with the response will be only sinusoidal or sinusoidal with a frequency of omega n, with a frequency of omega n. So, if you plot x versus t, so this will be sinusoidal with frequency of omega n, where omega n equal to root over k by m. Now, by adding this damping, so the system can be modeled as a underdamped, overdamped or critically damped system, and one can study the response of the system. So, for example, in case of underdamped system, so the response will be oscillatory. In case of critically damped, it will take minimum time to reach the equilibrium position, and in case of overdamped system, so it may not reach that critical value, or the system will be overdamped depending on the value of C. Now, by putting this nonlinearity, so today class we are going to see how the effect will be there. if we take different value of this m, k, k1, c and f. So, these are the recent paper which you may go through. For example, this last paper, this paper also periodic solution of discontinuous Duffing equation. So, you can have a continuous. So, this equation you have seen. So, you can have a discontinuous Duffing equation, means discontinuous type of forcing. The forcing, if so, for example, you just take the forcing that of a frictional. So, if you have a friction acting on the system, so in that case, or if you are taking a forcing. So, if you remember the Coulomb type of, so this is your minus mu n, so this is mu n. So, Coulomb damping, if you remember the Coulomb damping, then this forcing you can write. So, this F t, the forcing, you can write this forcing F equal to, so F equal to mu n signum x dot. So, here, so when x dot greater than 0, so it takes a value of mu n. So, if x dot less than 0, it takes a value of minus mu n. So, when x dot equal to 0, so it jumps from minus mu n to plus mu n. So, the system is not linear in this case. So, there is a jump from minus mu n to plus mu n. Similarly, so if you can take a system with different type of stops, then also the response or the forcing may not be continuous, it may be piecewise continuous, or discontinuous, it may be discontinuous. Like here it is discontinuous, it jumps from minus mu n to plus mu n. Similarly, you can design many systems, or there are several physical systems. So, where the forcing may not be continuous, so it may be discontinuous. So, here another paper, nonlinear vibration of doping system under combination of a constant excitation and harmonic excitation. So, you just see, so there is two different type of excitation is given. So, one is constant term and another is harmonic excitation. So, we can see many other papers also, some more papers are here. So, broadband energy harvesting based on 1-to-1 internal resonance conditions. So, all of you now by this time you know what is external excitation. So, if you apply external force to the system, that is external excitation. So, many systems will have, for example, let me take a 2 degree of freedom system, this is one spring and mass, let me take another spring and mass. So, this is M1 and M2, M1 and M2, or let me take a cantilever beam, or that is a continuous system. So, in this system, let this is the forcing applied here. So, this is the force applied here. So, let this force equal to F cos omega t. So, as this is a 2 degrees of freedom system, so you know, so it has two frequencies, two natural frequencies. Similarly, in these continuous systems, so it will have infinite number of natural frequency. So, for example, so if we take the simply supported beam, simply supported, so one side it is hinged and other side it is a roller support. So, this is a simply supported beam. So, in this case of simply supported beam, so you know the formula for this thing, this can be modeled as a Euler-Bernoulli beam, where this omega n can be written as beta square L square root over E I by rho L fourth, E I by rho L fourth, where this beta L equal to, so where beta L equal to n pi, so for the simply supported beam. So, for n equal to 1, so this becomes beta L equal to pi. So, the for first natural frequency becomes pi square root over E I by rho L fourth. Similarly, for omega 2, so this is 4 pi square and into E I root over E I by rho L fourth. So, that way we can get different natural frequency. So, the system has infinite number of natural frequency if the system is a continuous system, but for this 2 degrees of freedom system, so it has two natural frequency. Sometimes if the natural frequency are in integer relationship, that is omega 1 or omega 2 is to omega 1. So, if it is equal to 1 is to 1, in case of tuned vibration observer, actually this condition is maintained, that is omega 2 is nearly equal to omega 1 and it is kept near to the excitation frequency. So, that the primary system, the motion of the primary system is completely observed, but it can be taken in different ratio also. So, for example, omega 2 is to omega 1 can be taken 3 is to 1, or it can be taken in different order. So, in this type of cases, when the relation is integer type, then generally energy transfer. So, when you are exciting one mode, the other mode got excited due to internal resonance. So, this is the condition for internal resonance, that means the natural frequencies must be in integer relationship. So, if they are in integer relationship, sometimes due to interaction due to this nonlinear forcing or nonlinear terms. So, some energy get transferred from the excited mode to the other modes. So, that is why the energy transfer takes place between the modes. So, this gives rise to different type of resonance, and that type of resonance conditions are known as internal resonance condition. Internal resonance condition. So, particularly in case of continuous systems, as there are infinite number of natural frequencies, many times some of the natural frequency are in integer relationship. Also, by providing different boundary conditions or the support conditions, or by making the structure in different way or the configuration topologically, one can make the structure in such way that one may get these internal resonance conditions. So, there are several papers available. For example, in this paper the authors have taken 1:1 internal resonance condition. So, you can see this next paper, that is parameter estimation of fuzzy forced doping equation, numerical performances by extended Runge-Kutta method. So, you just see you can use already we have discussed that by numerical method you can solve these equations. So, Runge-Kutta method can easily be used for finding 4th order 5th order. Runge-Kutta method can be easily used to find the response of the system by numerically solving this first order differential equation. So, if you have a second order differential equation, first you convert that thing to a set of first order differential equation and then apply this Runge-Kutta method to find the solution. Nonlinear energy harvester with coupled doping oscillator. So, in this paper, this for a energy harvester this doping equation is used. So, here it is written coupled doping oscillator, that means the, so in case of the energy harvester, so two things are there. So, one is, for example, this cantilever beam can be used as a energy harvester. So, where this piezoelectric one can put this piezoelectric pads, and so the motion of the cantilever beam will give rise to a forcing or strain in the piezoelectric pads, which give rise to the voltage in the system. So, you have two different equations, one equation for the displacement of the cantilever beam and second equation is the voltage equation. So, there is a coupling, if there is coupling between this voltage equation and this beam equation, so then it is a coupled doping oscillator. So, in this case, so you are getting a coupled doping oscillator. So, the generalized doping oscillators, so you can see this paper, a generalized communication in nonlinear science and numerical simulation. So, how this doping oscillator, generalized doping oscillator is solved, those things have been discussed in that paper. So, also you can see some paper like this, the primary and subharmonic simultaneous resonance doping oscillator. So, primary resonance occur when your external excitation frequency, for example, this is external excitation frequency f cos omega t. So, when this omega is near to, so when omega is near to the natural frequency of the system, for example, in this case you have n number of natural frequency, and when the external forcing external frequency equal to the any of the natural frequency, then you can get the primary resonance. Then, so two, particularly in case of the nonlinear systems, two more different type of resonance conditions you may see. One is the supercritical and other one is the subcritical resonance condition. In supercritical resonance condition, so this omega will be equal to omega some fraction of the natural frequency, and for example, this omega may be equal to omega n by 2 or omega n by 3, omega n by 3. So, in these cases, so it will be supercritical or superharmonic resonance conditions. Similarly, this omega may be equal to 3 times omega n or 2 times omega n, depending on if the system is having cubic nonlinearity or quadratic nonlinearity. In that case, you can have the subcritical resonance conditions. So, particularly in case of these nonlinear systems, we will be interested to study, so all these resonance conditions. Sometimes two or more resonance conditions can occur simultaneously. So, that is why you can see the simultaneous resonance conditions written here. Primary, so both primary and subharmonic resonance conditions are occurring at the same time. So, that is why in this paper, so these primary and subharmonic resonance conditions, simultaneous resonance conditions have been discussed. Similarly, one can apply the stochastic type of forcing. So, in stochastic type of forcing, one may apply this stochastic averaging for single degree of freedom strongly nonlinear system under combined harmonic and Poisson's white noise excitation. This is discussed in this paper. So, there are several papers available, but I have shown some sample papers which are published in this 2000 and going to published in 2020 and 2021. So, only this paper in 2020 and 21 have been shown. So, you can go through some recent papers also which are published in different journals related to nonlinear vibration. Okay. So, let us see the doping equation. So, the doping equation can be written in its generalized form. You can write this u double dot plus omega 1 square u, or omega, generally it is written omega n square u, that is natural frequency square of the natural frequency into u plus 2 epsilon mu u dot. So, if we are assuming the damping, generally the damping is 1 or 2 order lower than that of the linear term, that is why this bookkeeping parameter epsilon is used here. Then this quadratic nonlinearity, you may put a quadratic nonlinearity epsilon alpha 2 u square, then a cubic nonlinearity epsilon alpha 3 u cube, and then the forcing term. So, if we are assuming the forcing to be weak, then this epsilon term can be used here. So, if it is not weak, so in that case it can be written as f cos omega t. So, in this case the forcing term, for example, if your omega n, so for example, if omega n equal to 1, so this forcing f also the magnitude of omega, if this omega n square value is 1, then this f also should have a value near to 1. So, in that case we can tell the system is strongly nonlinear, strong forcing, and if you are using this epsilon, then the system is weak forcing, the forcing term is weak. So, later we will see that when the forcing is very strong, so in that case we can have, so this already what I told you, that is primary resonance condition. Then we may have the secondary resonance conditions like subharmonic and superharmonic resonance conditions. So, all these type of resonance conditions we will see. So, if the system is will have the strong forcing. So, initially we will see the free vibration, that is when f equal to 0. So, already we have seen these examples when we solved or we have taken the application with different perturbation methods. So, you can solve this numerically or you can use these perturbation methods. So, let us see, already we have seen this thing, but we can revise this part by using this Lindstedt-Poincare method. You can use the modified Lindstedt-Poincare method also, or other type of methods like averaging method, method of multiple scales to find the solution. So, when this f equal to 0, so when f equal to 0, that is the free vibration part, free vibration. So, in case of free vibration, so we will see, so in case of Lindstedt-Poincare method, so generally we write the equation in this form, that is tau, we take tau equal to omega t, and omega is non-specified function of epsilon, and this omega we are taking equal to omega 0 plus epsilon omega 1 plus epsilon square omega 2. So, till now this omega, neither omega nor this only omega 0 is known to you, omega 0 equal to root over k by m, other terms are not known to us. So, the solution, so in Lindstedt-Poincare method we will take this omega this way, and then this x t equal to epsilon x 1 plus epsilon square x 2 plus epsilon q x 3, and if you have this forcing term, then you can add this x 0 term also. So, if there is forcing, then you can add this x 0 term, because in case of forcing, so the response will be non-trivial. So, generally it will be non-trivial response. So, some response amplitude will be there, but if there is no forcing, continuous forcing to the system, the response due to the presence of damping or nonlinearity, it may come to the trivial state, that means finally it may come to 0. So, if you are taking this equation in this form, that is d square x by dt square plus alpha 1 x plus alpha 2 x square plus alpha 3 x cube up to cubic order, if you are taking, then this alpha 1 equal to omega 0 square. So, now by substituting that previous equation, so we can write this equation in this form, that is omega 0. So, first what we have to do, so first we have put this tau equal to omega. So, you just see we have put tau equal to omega t. So, d square x by dt square, d square x by dt square equal to d by dt. So, already we did this thing, and again let me revise this thing. So, dx by dt, so this is equal to d by dt of, this is d by d tau into, so dx by d tau into d tau by dt. So, this way this term is omega, again if you are doing this thing, then omega square. So, this will come to omega square d square x by d tau square. So, this omega square term will be multiplied, so which is written here. So, this is again this omega can be written as omega 0 plus epsilon omega 1 plus epsilon square omega 2, this whole square d square by d tau square, and for x you can substitute this thing, and for this one, so you can substitute for xn, you can substitute this. Now, by separating of the different order of epsilon, so you can write this d square x 1 by d tau square plus x 1 equal to 0, similarly plus omega square into d square x 2 by d tau square plus x 2 equal to minus 2 omega 0 omega 1 d square x 1 by d tau square minus alpha 2 x 1 square, and similarly the third equation can be written in this way, and the solution of the first equation, so you know, can be written this x 1 equal to a cos tau plus beta. Then substituting this x 1 in this equation, you can find the expression for x 2 and substituting. So, here you can see when you are substituting that equation, so there will be some terms, so the solution of which will leads to the response to infinite, but actual case the response is bounded. That is why So, those terms are known as secular terms, and one must eliminate those secular terms, so that one can get a bounded solution. So, in this case, so you can see this omega 0 square into d square x 2 by d tau square plus x 2 equal to 2 omega 0 omega 1 a cos tau plus beta. So, here the coefficient of tau equal to 1 and the coefficient of x 2 equal to 1. So, that is why, so if you take the particular solution of this one, so in the denominator, so denominator your it is becoming d square plus 1, as in the denominator d square plus 1, and you have a cos term here cos tau plus beta. So, as the coefficient is 1 here, coefficient is 1 here. So, you have to substitute this d square equal to minus 1, d square will be equal to, so this omega, so this is omega t. So, it will be replaced by minus omega square. So, minus 1 plus 1, this tends to infinite. So, this tends to, so this part tends to 0. So, as this part tends to 0, the whole term, this whole term tends to infinite. So, this leads to this particular integral tends to infinite. So, the solution, so this term is a secular term and it must be eliminated. So, as you know, this cos term has a plus maximum value of 1, and so it cannot be 0. So, and omega 0 is not 0. So, a equal to 0 will lead to trivial solution. So, so if you require a non-trivial solution, here omega 1 must be equal to 0. So, by making omega 1 equal to 0, only we can eliminate the secular term. So, this way the term omega 1 we have determined. So, now by putting this omega 1 equal to 0, so we can write the solution of x 2. So, in the solution of x 2, so the particular solution only we can write. So, particular solution will contain by putting this omega 1 equal to 0. So, we get this particular solution, that is x 2 equal to this. So, how to get this particular solution? So, this term has already gone. So, this term divided by d square plus 1 into omega 0 square. So, for d square, so you just see it has two parts. So, this is the constant part and this is the cos part, cos 2 tau omega t. So, in case of cos 2 tau, the coefficient is 2. So, you can substitute this d square by minus 4. So, minus 4 plus 1, so this becomes minus 3. So, this is the term you got, and for the first part, so you can take this d square plus 1 to the numerator with to the power minus 1. So, this becomes 1 minus d square, 1 minus d square of this term, whole term. So, in that case differentiation of a constant, so only the constant term will be there, the other part will be 0. So, you can get only this term, that is minus alpha 2 a square by 2 omega 0 square. So, the x 2 can be retained in this form. So, now by substituting this x 1 and x 2 in the third equation, so you can get this one. So, here again you have to check the terms which are secular term. So, the coefficient of this cos omega, the cos t tau plus beta is the secular term. So, this term is the secular term. So, now by eliminating these secular terms, so you can find, so this term can be eliminated. So, if this is equal to 0, so from this thing, so you can get omega 2. So, now after getting this omega 1 and omega 2 and keeping this omega equal to up to that thing, that is omega 0 plus epsilon omega 1 plus epsilon square omega 2. So, which we have assumed in the beginning. So, omega equal to omega 0 plus epsilon omega 1 plus epsilon square omega 2. So, now we can get the solution. So, that is omega equal to this. So, here you can note, or this is an assignment to you. So, you can plot. So, you can see this omega is a function of a, omega is a function of a. So, unlike in case of linear system where omega is not function of the response amplitude, in case of the nonlinear system the frequency of oscillation the frequency of the response depend on the amplitude of excitation, amplitude of the response. It depends on the amplitude of the response. So, you can plot the relation between, or you can plot this A versus omega, and so from this equation. So, by using this equation you can plot A versus omega, which is known as the frequency response plot, frequency response. Okay. So, this way you can find how the frequency is related to the response amplitude, and this is the free vibration response of the system. So, already we have discussed regarding this Runge-Kutta method, fourth order Runge-Kutta method. So, in this case, so this equation, so you can write your own equation. For example, so if you have been given a differential equation, first order differential equation in this form, that is dy by dx equal to f x y, and the initial conditions are given to you. So, you can find by using these 4 equations, or using this equation with the 4 coefficients k1, k2, k3, k4, where h is the step size. By taking different step size, so you can find the y k plus 1 in terms of y k. So, that means you can find the response of the system by using this method. So, you can write your own code by using these equations, or you can use different functions available in different softwares. For example, in MATLAB. So, in case of MATLAB, so you have this ODE 45, ODE 23, ODE 15. So, different methods are there for different types of equations. Sometimes the equation may be stiff. So, sometimes the equations may be of different type. So, depending on your equations, so you can use different type of function. Similarly, if you have a delay differential equation, so you can use this dd instead of ODE. So, you can use this dd, delay differential equations. So, later we will see one example of delay differential equation in case of the doping equations also. So, if you have a equation like this, for example, x dot plus x equal to, so you can take for example x double dot plus x equal to 0. So, you can take y1 equal to x and y2 equal to, okay, y1 equal to, so if depending on the equation. So, this is a first order equation. So, you can dy1 equal to x double dot. So, you can find, so you can write 2 differential equation and you can solve it. So, these are the response, already we have seen this thing. So, now let us see. So, if you have any generalized equation d square x by dt square plus fx equal to 0. So, always you can write this equation by using 2 first order equation. For example, if you are taking this dx by dt equal to y, then this dy by dt will be equal to d square x by dt square, which is nothing but minus fx. So, this way you have written 2 first order equation for a given second order equation. So, now if you linearize these equations, or linear form if these equations can be written, so you can write this dx by dt equal to ax plus b. Similarly, this dy by dt equal to cx plus d. So, if you assume the solution of x, for example, let us assume the solution x t equal to a e to the power lambda t and y t equal to b e to the power lambda t, then these 2 equation, this dx by dt will be equal to a lambda. So, you can write this, let x equal to a e to the power lambda t and y equal to b e to the power lambda t. So, in this case dx by dt will be equal to a lambda e to the power lambda t, and similarly dy by dt. So, this will be nothing but this is b lambda e to the power lambda t. So, so this is equal to a e to the power lambda t equal to x. So, this becomes lambda x. So, this becomes lambda y. So, So, in this case, so if it is dx by dt, so for dx by dt we can write this is lambda x equal to ax plus b or a minus lambda into x plus b equal to 0. So, this equation reduced to a minus lambda into x plus b equal to 0. Similarly, here also we can write this b. So, this is c minus lambda x plus d equal to 0. So, this way we can write these two equation. So, then we can write, so or we can write this in matrix form, that is a minus lambda b c d minus lambda. So, this must be equal to 0. So, for non-trivial solution, for non-trivial if x not equal to 0, so that is non-trivial solution. So, for non-trivial solution, so for non-trivial solution, so when that is x not equal to 0, so a minus lambda b c d minus lambda equal to 0. So, if you take the determinant of this thing, so a minus lambda into d minus lambda minus bc equal to minus bc equal to 0. So, this thing can be written in this form, that is lambda square minus trace lambda plus determinant equal to 0. So, here, so for this, by solving this thing you can write this lambda equal to trace by 2 plus minus root over trace by 2 square minus determinant. So, here trace equal to, so this trace equal to this plus this, your matrix equal to a b c d. So, trace becomes a plus d and determinants becomes a d minus b c. So, this way, so trace become a plus d and determinant becomes a d minus b c. So, depending on, so actually depending on this factor, so this root over inside this term. So, if it is real, then you can have, depending on the nature of the response of this thing. So, you can have different type of lambda. So, lambda may be real, it may be complex. So, in case of the real, so the real part may be positive, the real part may be negative. So, all or we know, so if the eigenvalues lies in the left hand side of the S plane, so this is S plane, so this is the real part, this is the imaginary part. So, we know that, so if this eigenvalue lies in the left hand side of the S plane, that means it becomes negative, then this will be e to the power minus this lambda is negative. So, the response will, decay, but if this lambda is positive, the response will exponentially grow. So, if the response will exponentially grow, so then the system becomes unstable. So, we must, to have a stable system, so we must have this real part of the lambda must lie in the left hand side of the S plane. So, if it is lying in the right hand side, any of the eigenvalue is lying on the right hand side of the S plane, then the system becomes unstable. So, this way you can see, for example, so if one plot this determinant versus trace, so this part is taken from the book by R. Rand, Nonlinear vibration book, nonlinear oscillation book by R. Rand. Okay. So, if you plot this determinant versus trace, so you can see we can have different type of response. In the previous case we have plotted this real part and imaginary part, but here we are plotting this determinant versus the trace. So, when you are plotting this determinant versus trace, so you can see if in the left hand, if it is in the left hand side, if the point in the left hand side, the you will get a response, so which is unstable. So, in that case, so if it is in the left hand side actually, so in that case, so it becomes positive, one of the eigenvalue real part will becomes positive. So, that is why you will get the saddle points, and so here also different type of things are there with examples I will show. So, one is your center, so then you can get stable spiral, stable node, unstable spiral, unstable node. So, depending on this T r square equal to 4 determinant. So, T r square equal to 4 determinant from this thing. So, this becomes T r square minus 4 determinant. So, this part becomes, so you can take this half outside. So, this becomes T r square minus 4 determinant. So, depending on T r square, if T r square greater than 4 determinant, then this part becomes positive and you can have real roots here. So, if this T r square less than 4 times the determinant, then this becomes, so the root over will be, so this is a negative number. So, the root over will be imaginary. So, in case of imaginary, so you can have the complex root. So, depending on the where it lies, if it lies in the left hand side of the S plane, then it becomes stable, otherwise it is unstable. So, let us take this example. So, for example, let us take this equation d square x by dt square minus x equal to 0. So, the auxiliary equation becomes d square minus 1 equal to 0, or so if you see, or d equal to d square equal to 1. So, d equal to d square equal to 1. So, d equal to plus minus 1. So, if d equal to plus minus 1, so the response becomes x equal to, so you can see the x equal to a e to the power. So, a e to the power, that is one solution is 1. So, this is t plus a e to the power t plus b e to the power minus t. So, due to the presence of this e to the power plus t, that means the response amplitude will grow with time. So, this part will reduce it, but this part will increase it. So, if you plot this x versus y, that is x versus x dot in this case, so you can find the solution or the response to be like this. So, it will exponentially grow. So, one part is, so due to the presence of this thing, so it is coming to this one to 0 line, but due to the presence of this part exponentially it will grow and it will go to infinite. So, this way it will start from infinite, so and this way it will go to infinite. So, you can find, so this point is the saddle node point. So, you can have a saddle node response. So, this type of response is known as saddle, or this type of point what you will get. So, is the saddle point. So, now let us take a equation this thing. So, this is similar to that of a free vibration of a single degree of freedom system. So, in this case, so you will get the spiral. So, it is spiraling into the system. So, you have a stable point, stable spiral point. So, in this case also, so you just see, so you have a stable point. So, here d square x by dt square plus damping plus x. So, it is spiraling here, but in this previous case, okay, so all the points are coming to the same point. And if you take this one, this is similar to that of a undamped system. So, here, so always, so this omega equal to 1. So, here omega square equal to 1. So, here, so you will have a response like this. So, this is the center. So, this is center. So, depending on the initial condition, so you can get different type of circles. In this way, so you can analyze a given equation, and you can find sometimes also depending on the coefficient. So, you may get the response to be chaotic. So, we will study the force vibration case. So, for example, already we have seen the force vibration case by using this method of multiple scales. We have taken several examples while we are solving these equations. So, for example, we have taken the equation, this is the equation we have taken, u double dot plus omega 0 square u plus 2 epsilon mu u dot plus epsilon alpha u cube equal to epsilon k cos omega t. So, this is the weak forcing type of thing. So, already you know, for the primary resonance conditions we can take omega equal to omega 0 plus epsilon sigma, and if we follow the simple procedure of method of multiple scales and eliminate the secular terms, So, we can get a set of equations. So, where A dash equal to minus mu A plus half f by omega 0 sin sigma t 1 minus beta, and A beta dash equal to 3 by 8 alpha by omega 0 A cube minus half f by omega 0 cos sigma t 1 minus beta, where the sigma is known as the detuning parameter. So, in this case you just see this is non-autonomous equation because it is written in terms of the time. So, to make it autonomous you can take the sigma t 1 minus beta equal to gamma, and this A dash and gamma dash equation can be written in its autonomous form, and again for steady state this A dash and gamma dash will be equal to 0 and you can have a set of equations. So, this mu A equal to half f by omega 0 sin gamma, and A sigma minus 3 by 8 alpha by omega 0 A q equal to minus half f by omega 0 cos gamma. So, by squaring and adding, so you can get a equation this, so which is sixth order in case of the amplitude and second order or quadratic in terms of sigma. So, writing a quadratic equation in terms of sigma, one can solve to get this equation sigma equal to 3 by 8 alpha by omega 0 A square plus minus k square by 4 omega 0 square A square minus mu square root over. So, one can plot the frequency response plot. So, a typical frequency response plot looks like this. So, here so you can observe that, so already just now I told you regarding the stability part. So, you can see that these branch, so in case of this type of system, so you have multi branch system. So, up to this you just see the response we have only single response, but here to here, so we have multiple response are there. So, 1, 2, 3, so we have 3 solutions are there. So, before this thing we have only one solution, and after this thing also we have one solution. So, we have multiple solutions between these two, this position, these portions. So, this is known as the frequency response plot. So, if we go on increasing the frequency, that is sigma is detuning parameter. So, by increasing sigma, so we are increasing the frequency, we can see at this point r. So, it will jump down to this response. So, because after this thing as it is not continuous, so the system will jump down from r to this point. Similarly, by increasing, so due to this jump down the system may break or fail. Similarly, by increasing the response, by increasing or decreasing the sigma, so it will follow this path, and at this position it will have a tendency to jump up. So, it will jump up here. So, you can have a jump up phenomena. So, you can have a jump up phenomena. So, from point P, so it will jump from P to Q, and then further decreasing. So, it will follow this path Q, then M, and it will come back this. So, due to this jump up or jump down phenomena, the system may have catastrophic failure. So, next class we will discuss more on this jump up and jump down phenomena, and we will study the if the forcing is strong. So, in that case also we will see simultaneous, if there is some simultaneous resonance conditions or subharmonic or superharmonic resonance conditions. So, thank you very much.